Okay, and this is working. Okay, so we're starting a little late, so I'll try to aim somewhere around 5:15 for questions, maybe even a little bit earlier. But yeah, I'm Zane. I currently am a postdoc at the University of Tokyo, and previously I was a graduate student at MIT working with Ike Chuang. This title is pretty broad, and I'm going to talk just about a subset of quantum algorithms, which seem to be quite useful for both sort of summarizing and mimicking other quantum algorithms that we know about, and are very good at sort of determining the complexity of manipulating matrices on quantum computers. And for people who are more talented than I in machine learning, this might be of interest to you. So my goal is to make these techniques a little bit more familiar, because I think at least they make it a little bit easier to understand quantum algorithms as we've been studying them over the past 5 years or so. So yeah, the goal of today's talk is a little bit of motivation and a crash course in a simpler quantum algorithm that is called quantum signal processing, so about its origins and what it's used for. Then we're going to talk a little bit about the numerical side of this, which is important. Then something called qubitization, so how we extend this idea in quantum signal processing to something called quantum singular value transformations. This is a very efficient way to manipulate linear operators on quantum computers. And then I'll mention some about the applications that these algorithms have found. It's more sort of an algorithmic framework that makes it very easy to characterize how expensive some of these transformations are. And then I'll talk about sort of the limits of singular value transformation, what it's not good at mimicking, what we still don't understand, and some other approaches that have recently come up to solve some of these problems for very specific but also useful tasks. And then we'll open this with sort of my outlook. And the reason I've included these colors is because I have this large diagram that's going to appear many times. Don't stare at it too hard. This is sort of just for vibes. I also have a copy of these slides on my website, and I'm sure they'll also be posted somewhere by QTML, because these are all hyperlinks that link to the papers that are there and included. But sort of the major portions of this talk are going to be according to these colors. So the first red is about the history of these algorithms and their original instantiations. Green is about their applications to various common problems like estimation or Hamiltonian simulation. The blue is sort of the numerical side, so people who are really interested also in the mathematical theory of how these algorithms work, or this class of algorithms more honestly. And then yellow is sort of adjacent algorithms that also manipulate a type of quantum data structure that we're going to talk about called block encodings. Cool, so we're going to start just with the red section here. The history of quantum signal processing is pretty old. It starts in nuclear magnetic resonance, so maybe there are experimentalists in the room. I am not, but I'm at least friendly with a lot of people who are. You know, NMR can be very complicated, but the basic idea is that you have some nuclear spins, they're in some magnetic fields, and you're allowed to hit them with radio pulses, and you want to learn something about the spin or magnetic field, etc. And one of the sort of basic questions of this is that if you have sort of many copies of, say, an unknown but consistent unitary process, say the result of letting your spins persist in your unknown magnetic field for a certain amount of time, what can you do with many of these processes? And so, you know, the simplest version of this, imagine that you have single qubit unitaries here. V is some unknown but consistent unitary depending on a scalar parameter theta. And if you have many copies of this, you know, maybe you can turn it into some other unitary theta, which has nice properties. And so a simple example from an old paper, this paper by Wimpers in 1994, proposed a whole bunch of these protocols, one of which is called the Broadband 1 protocol, the BB1 protocol. And ignoring for the moment how this works, so I'll talk about it later in terms of QSP, here you have some probability of measuring, say, the spin up state after evolving for a certain amount of time. And they showed that, you know, if you do this naively with just, you know, waiting for one period of the precession of the spin, then depending on this sort of unknown parameter theta, which you can think of as, say, a magnetic field strength, the probability of measuring one has some Rabi oscillation. And so they showed by using sort of many of these rotations together in a creative way, they could have it be such that, you know, around theta equals 0, so around a variety of magnetic field strengths, the probability of measuring one was almost constant. So they used this because they wanted to help remove inhomogeneities in magnetic fields, but we're going to use it in a slightly more creative way to help us manipulate linear operators on quantum computers. I guess that's sort of the history, and you can see that this has really been a long process. So 1994 was when they were talking about these composite pulse sequences, and even in 2004 with a paper of Haro and Chuang, they were talking about sort of better ways to design these for error suppression, and then the papers for QSP will be in 2014. So, you know, even though these are, you know, seemingly simple ideas, it takes quite a long time to develop these algorithms. Okay, so what is quantum signal processing? You know, abstractly, you can think of it as a nice way to design these SU2 valued functions, so unitaries on a single qubit. And the idea is that we're going to try to pick a list of real numbers. These are going to be called the QSP phases. And we're going to use these numbers to sort of program a unitary which depends on an unknown signal x. And being able to do this will end up being quite useful for a variety of other tasks. And our unitary oracle, so this unitary that we're allowed to apply that's consistent, depends only on this sort of unknown scalar x between -1 and 1, and it happens to be an x rotation. So it's a structured oracle. We know something about it. And I'll also explain why this is somewhat relevant. So this program of phases is going to allow this ultimate unitary to depend on the signal x in some complex way by a circuit that I'll draw on the next slide. And here is just sort of the nice computational basis representations of these two matrices. So you can imagine maybe in your head now, if I multiplied a whole bunch of these together, maybe what would the form be? So when we look at what this circuit is, it's as simple as possible. It's just a single qubit, and we're going to alternately apply this z rotation by some chosen phase phi, followed by this unknown rotation. Then we apply another known rotation, repeat this for as many times as we think is reasonable, and we'll end up with some state at the end. And it turns out that if you write out the entire unitary here, its matrix elements happen to be polynomials in this unknown signal x. And so the question then becomes, how easy is it to choose a polynomial that you'd like to implement and determine whether or not there exists a phi, and more importantly, actually compute the phi that achieves that polynomial. And there's sort of a secondary claim that we'll make later. This is qubitization. Don't worry about it too much now. Is that we're going to be able to replace this scalar value with a matrix, say like a normal matrix or Hermitian matrix is the easiest, to do things with these large block unitaries. So you can see why that would be useful later, but for now we're just going to talk about the single qubit case because its mathematical behavior sort of defines everything that you can do in this block unitary case. So that's what we'll discuss later. But is everyone good on the definition of the circuit? It's just x rotations and z rotations. We don't know the x rotations, but they're consistent, and the z ones we can choose. Okay, so this BB1 protocol that I mentioned before, if I write it out as one of these QSP sequences, here v is some x rotation by theta, and then I choose a whole bunch of these eta-dependent z rotations, and if I write out this matrix and compute what p is, I get this very complicated polynomial, and if I were to plot this out, you would have seen the previous plot where it gets very flat around theta equals 0. And we can see this, here I'm mapping a little bit wantonly between theta and x. Theta here is the arc cosine of x for historical reasons, but around theta equals 0, this is very flat. It has theta to the 6th behavior. So that's just a concrete example of that simple protocol. Okay, so the big question is, what are the achievable polynomials in this picture? And let's see. Basically, the idea is that we're going to be able to choose some components of this unitary freely, and being able to choose these components freely is still quite useful from an algorithmic standpoint, and the constraints are sort of not so complicated. So I'll take two real polynomials. Let's just say that c of x is 0, and then I know that the norm of a of x is bounded above by 1 on this interval -1 to 1, and I'll also know some things about their parity. And if I were to do this based on this previous parameterization, you can compute this by yourself. The probability of measuring, say, the plus eigenstate after starting in the plus eigenstate is just the square of the modulus of A. And sort of the proof method and the way that people traditionally prove things about QSP is that first you're going to specify these components. You're going to do a process called completion, which is basically finding the remaining components, and the existence of these depends on the fact that C and A satisfy these criteria. And then you'll do this process called layer stripping, which inductively reads the phi off these phases. And there's a bunch of other parameterizations and ansätze that you can consider. For instance, you can think of this not on -1 to 1, but on the real unit circle in the complex plane. And all of these sort of slightly change the statements of these theorems, and different people have different preferences. But overall, these constraints are simple, and they relate to simple sort of observable probabilities, which is nice to be able to design. So more concretely, we know that this whole SC2 object is going to be unitary, so we know there's this non-trivial relationship between P and Q. And we also know that if you have a circuit of length d, namely you apply this oracle d times, these polynomials have degree d. So the basic constraints for this full case is that the polynomials have degree d, they have definite parity, and there are these constraints at x equals plus or minus 1 and 0 that just depend on symmetries of the ansätze. And this gets even simpler if you do this parcel specification, so just the real parts of the on and off diagonal elements of this unitary. because they just have to satisfy this inequality. And as I mentioned before, you can choose c equal to 0, which means that basically any definite degree polynomial, which is norm bounded by 1 on the interval, can find its way as the real part of this matrix element. So it's very easy to characterize the achievable polynomials in this simple setting. There are other ways to circumvent some of these constraints, like this parity constraint. There are many papers that have since looked at ways to, either with additional space or giving some more freedoms as to, not just z rotations, but arbitrary SU2 rotations, remove some of these constraints. So it's very easy to design these protocols. And as I mentioned before, finding these reduces to this norm-constrained polynomial interpolation, which for the functional analysts out there is something in one variable that we know how to do very efficiently. Okay, now I'm going to talk a little bit about this sort of set of numerical work on the side, going from the more concrete to the more complex. And the goal of a lot of this work originally was to make sure that the algorithms, the classical companion algorithms for computing these phases, so I give you a polynomial you want to find, and you want to compute the QSP phases, this list of real numbers that achieves that polynomial, to make sure that these classical algorithms are numerically stable and efficient and all of that. So there's been a whole bunch of work from many different groups, starting with Jungwon Ha, and a lot of work from the Lin group at UC Berkeley, basically answering this question in the affirmative and that there's no real problems in computing these phases. And so the typical order that you go in is you start with some desirable continuous function you want to approximate, this f and g. You find these partially specified polynomials a and c. You convert these through completion to p and q, and then you read off p and q via this inductive layer stripping argument. And this is all with SU2 unitaries. You can write it out in just a few lines. And so there's not too much going on here. Sort of alternatively to this, and with some of the same authors, people have looked at sort of just straight up numerically optimizing over these protocols. And so remember that everything here is a 2x2 unitary. The quantum hardness, or the classical hardness of these algorithms is not going to come until later. But even sort of these simple Newton-type method iterative schemes to iteratively optimize over phases that, say, achieve some desired A, depending on a simple calculation of the inverse of the Jacobian, also work extremely well. So sort of numerically, you have to prove a lot of things, which is what these papers have done, but these algorithms are not so hard to deal with numerically. And there's a whole bunch of other things people have done connecting these algorithms to a topic called nonlinear Fourier analysis. But basically, sort of as long as your function that you're trying to approximate has its infinity norm on the interval bounded above by 1, and they talk about a particular class of functions that has a very technical definition called Segu functions, then these iterative schemes can be proven to converge very fastly. So this is a numerical interlude, but just don't worry about these things. So on the numerical side, it's very interesting to talk about, and in future settings where you're trying to change around this ansatz, it might be useful to go into this work again or extend it. But for our purposes, just assume that numerically behind the scenes everything is okay. And then there's packages for dealing with these things if you want to play around with actually computing QSP protocols. One from the Lin group called QSP Pack, and one from my advisor's group that I guess I'm the active maintainer on, so if you send a pull request, I will receive it, called PyQSP. Okay, so we're going to pause and talk about what QSP has told us to do. So we know that QSP can sort of usefully characterize these SU2 valued functions, and we know how to specify a polynomial and compute the phases. But what we really want to do is not talk about transforming a scalar. We want to talk about transforming systems consisting of many qubits, because the Hilbert space needs to be of large dimension if we want anything to be classically hard. So now we're going to build up the intuition for how we take ideas in QSP to talk about quantum singular value transformation, which ends up being useful for a large variety of problems. Yeah, so we need to find these qubits that we're talking about, these SU2 spaces inside of large unitaries. I claim that we've done this before. One of the first quantum algorithms we all learn about is Grover's algorithm. And a key insight of Grover's algorithm, maybe you wouldn't learn about it this way at the time, is that the ability to reflect about quantum state, say like an unknown quantum state, is extremely powerful. And there's also this statement here, this paper by Jordan in 75, that's in 1875, so it's a very old paper, that the product of two reflections generates a rotation. And so, in the Grover world, you have this marked state T, and you have some subspace here, which is all the, spanned by all the states which are orthogonal to T, and you also have this other state here, which is the uniform superposition, and you are alternating reflections about the marked state and the uniform superposition, and somehow, if you learn about Grover's algorithm, this drives your state towards the marked state. And the way that you go about proving this is that you can take these two subspaces, the marked state and the perp space, and you can also rewrite this in terms of this S state and its perp space, and then you can write out what's called the Grover iterate as a SU2 operation, or I guess maybe in this case just a two-dimensional operation between these two different subspaces. So the one here with the -1 here, this is the marking oracle, which just applies a phase, -1 to the marked state, and then this rotation about the uniform superposition has some other complicated behavior, where C here is going to depend somehow on the overlap, so you see up there, between your marked state T and this uniform superposition. And it's efficient to rotate about the uniform superposition because we can easily prepare it, and it's efficient to rotate around S because that's what Grover's oracle is assumed to do. Okay, so with this sort of insight, the world of Grover iterates, there was some other papers that came out from Yoder, Low, and Chuang in 2014 that basically says, okay, well, I can reflect about these states, so if I rotate by an angle of pi, but why not sort of reflect not by pi, but some smaller angle here? So you can imagine now that I have two axes in the block sphere, and what if I gave myself the ability to apply a phase between these two subspaces? So here I can rotate by an angle beta around the marked state, or an angle alpha around this uniform superposition, and what can I do if I can do these things arbitrarily? Maybe I can achieve behavior that's slightly more interesting than just Grover's algorithm. But this is already a simple instance of what we're going to call qubitization, where these are multi-qubit systems, multi-qubit oracles, but somehow the behavior is being summarized entirely by a single block sphere. Okay, so now I'm going to define block encoding, and I'm going to be very careful at the beginning of this, and then we'll get a little bit fast and loose later. But for the people who really care about matrix dimensions, we have some, in this case, arbitrary, possibly non-square linear operator A. This is R by C. Then we're going to have two parameters, alpha, which is a subnormalization, and epsilon, which is some precision. And then we're going to have these two other operators here, which have orthonormal columns, and these are going to somehow, they have respective dimensions here. They're going to help us locate subblocks of a larger operator U, which contains A. So when we say that we have a block encoding, sound working? Cool. Yeah, so by a block encoding of A, we're going to say that inside this larger D by D unitary, located by these BL1 and BR1 operators, there is a copy of A possibly subnormalized by this parameter alpha, and everything is in the operator norm up to precision epsilon. So we'll write out a nice little picture of this later. But you can think of U, this large unitary, and some subblock of it contains A. And this can always be done with something, at most basically twice the size of the largest dimension of A, as long as A has spectral norm bounded above by 1. And so, yeah, people get very technical about this. You can define BL and BR, which are these unitary extensions of these BL1s and BR1s. And all this is covered in this wonderful paper by Tian and Tang about the cosine sine decomposition. But if you play around with these operators, then it's just a nice way of talking about subblocks of unitaries in a very concrete way. Okay, so there's other definitions that people give for block encodings. So this other foundational paper by Guillen, Su, Low, and Wiebe in 2019 expresses it in a more quantum notation. And so here they just say that if we restrict to everything being in the computational basis, if those B, L, and BRs previously were just diagonal with only ones on the diagonal, it would look something like this, where if I post-select basically on starting in the 0 state and ending in the 0 state, I get something which looks like A. And this is how these algorithms are going to be useful. It says that if I start my whole state in some 0 state on these A qubits, I evolve and I post-select on this 0 state, I will have applied something which looks like a subnormalized version of A to my quantum state. And they have this extra parameter S, which says how many extra qubits you've used for the block encoding. And in our case, this pi L will just be this projector onto these 0 states in that register. Some people just sort of drop all these extra dimensions, and they say that pi L and pi R multiplied by A, multiplied on these sides of U is equal to A, but if you look at the definitions previously, the dimension doesn't quite match, and we're just ignoring a lot of 0 subblocks. But now we're going to talk about the singular value decomposition of A. All linear operators have singular value decompositions, which makes it quite nice. And everything I'm talking about here is going to map from this non-tilde space to the tilde space. So what does A do? It says that I take psi I tilde, I map it to I take psi I, I map it to psi I tilde, and I have this factor of xi, which is my singular value, which is positive and somewhere between 0 and 1. And so we can look at sort of the action of this unitary on one of these singular vectors, and you can see that I can insert a pi r between u and the action of that, and I can expand the identity operator in terms of pi l and 1 minus pi l, this projection. And so I see that I get xi times this psi I again, and then I get some other mysterious state, which I've preemptively put in this mysterious factor of the square root of 1 minus xi squared. So the goal of qubitization is basically to figure out how to make that other state something useful and be able to map back and forth basically between the right singular vector space and the left singular vector space corresponding to each singular value in a way that looks like a qubit. Okay, so as before, basically we're going to break down the overall subspace into many tiny pieces, and then the original argument goes by showing that each of these subspaces is suitably pairwise orthogonal. So basically, Ci is the ith singular value, and then we're also going to have the ranks of both of these operators, left and right singular vectors, and basically the nice thing is that these singular vectors are just the bases for the images of these projectors, and usually the image of the projector will be very easy to prepare. It's just like the projector onto 0 and all of the first a qubits followed by sort of the identity. So I'm going to define these new perp vectors, and these are going to be analogous to the t perp in the Grover case. And these are going to be basically proportional to what happens when I say, okay, I apply u to this singular vector. That gives me something which is a tilde singular vector, so it takes a right singular vector to a left singular vector, and then I'm going to project onto, outside the image of this PL. And this will give me something which is necessarily perpendicular to the tilde version, this left singular vector. So I'm basically making up these subspaces such that the computations I do later will make sense. And this is the same thing you do in the Grover setting of, naming these subspaces to do what you want. So we define all of these nice subspaces, and the only ones I want you to care about are the red and green ones, which is basically the ones where the singular value is not 1, so it's somewhere between 0 and 1, and you'll have hi tilde, which is the span of this perp left singular vector and the left singular vectors themselves, and you'll have this hi, which is the same with the right singular vectors. And then we're going to try to prove that the action of u on these subspaces is very simple, and in fact just looks like a direct sum of qubit-like actions. Okay, so we need to show that all these subspaces are orthogonal, and I'm not going to spend too much time on this, but you basically go by case, and we already know that singular vectors are orthogonal within themselves unless their index is the same, and then you're also going to show that basically the same is true of the perp vectors, which follows by the fact that u and pi is what relates these singular vectors to their perped versions, and then basically everything else necessarily is just going to be 0. So all these identities just go through by replacing these perped versions by their definition in terms of u, and these basically projections outside the image of pi r and pi l. And this basically means that everything is going to be able to be written as a direct sum. Okay, so at the end of the day, what you get is that the action of u, so this overall unitary that you have, which has this block structure corresponding to these projectors, is going to have this direct sum of two-dimensional transformations, and these transformations are going to look like rotations by this singular value, really the arc cosine of the singular value. And then what we're going to do is we're going to construct basically these simple phased rotations here, which are going to apply a relative phase in this diagonal way between sort of these two states that have been located according to a singular value. And so then you can see that if I were to multiply these two operations together, with a little bit of extra work, because now I care about the left and the right singular vectors possibly being different, it's going to look exactly like quantum signal processing, but in exponentially many of these subspaces at once. And here, this notation, we're always mapping from the top index to the bottom index. So we already know that u maps right singular vectors to left singular vectors, and this pi here only maps the right to the right. So the whole circuit that people use, and I'll do a picture here from the Gillian paper again as well, is that I have this list of phases phi, and then I have alternating products basically of u dagger, and then these phased rotations that depend on whether or not you're in the image of these projectors. And these projectors locate the subblock inside the unitary. And the result of all of this is, again, as I mentioned before, that you're going to have basically exponentially many copies of QSP happening in each of these subspaces, and this will induce basically a transformation of the singular values of this operator A that you've encoded in the unitary U. So this is the result, and if you look at each of these subspaces, this P that you get is going to be exactly the same P you would have gotten with the QSP phases phi. So yeah, a lot of indices flying around, and I'll talk after this with a slightly more straightforward way to see why these decompositions should even exist in the first place. This is what the circuit looks like, at least how it's commonly notated. So U and U dagger here are being alternated, and notice that they have to be alternated because U takes left to right, U dagger takes right to left, and this is sort of what closes these two-dimensional subspaces. And it's really quite important that you have access to U dagger, which is important for experimental applications later. Then you also have these projection-controlled knots, and what this does is says for in the image of this projector, in that lower set of qubits that I'm suppressing with this slash, then just apply a phase to this upper qubit, to which I apply this sigma z rotation. And you might wonder, okay, can I easily create these projection-controlled knots? And the simplest example will just be a C knot or a Toffoli, because usually the projection is just this tensor product of zero kets. Cool. Yeah.
Can you go back?
How far back?
This one's good, but also the previous one. Okay.
Yeah. I can relay your questions at least.
So the first block with you have your first index I and K. Are those 1-by-1 blocks or 2-by-2?
Yes, I'm being a little uncareful here. These are different I, but basically those C that are in the first block, so before K, the C is just 1. So basically,
okay.
or minus 1. So only one-dimensional subspaces.
So my question is, can you advance one more slide? Yeah, this one. Why does the polynomial P get applied in that first block if it's just a 1-by-1? Because isn't...
Yeah, I think here this is also somewhat artificial because the polynomial will have a constraint which states that it has to take value, absolute value 1 at 1.
Oh, okay.
But yeah, sometimes it can be a complex phase as well, depending on how you parameterize.
Okay.
But it's still one-dimensional, yeah.
Thank you.
But somehow you could treat these all with the same index if you really wanted. It's just to make it obvious that something special happens when your singular value is 1. Yeah, sorry. Yeah, a lot just happened here, so please ask me.
Can you clarify again these projectors pi r and pi l?
Yeah, so
do they depend on U or not?
So these projectors locate the subblock of U that you're going to want to use. But usually, these projectors are going to be very simple, like projection onto the zero, product of zero kets in some register that you have. So this projection-controlled knot that you're going to want to build often will look like a C knot, according to whatever auxiliary qubit you use to block encode the operator. So later we'll talk about when can I even build an efficient block encoding, because you can imagine that if I choose all of these exponentially many matrix elements, it's going to be very expensive to construct. But usually, yeah, these projections are going to be onto very simple subspaces. It's just in the most general case, you could also imagine that what if I had a unitary which prepared the state that I could then project around? So I wouldn't necessarily have to know what this projection is around or onto. But yeah, in general, it'll look like a C knot or a Toffoli. But the point here is you have sort of this global action with U, and then you have a very simple action on a single qubit in this upper register connected by this projection-controlled knot. And somehow this interface between the global action and this local qubit allows you to do very complicated things to these subspaces. Okay, cool. Yeah, there's another approach. This will be a single slide called the cosine sine decomposition, which I think everyone in quantum algorithms should learn about because it's had a lot of success in many different areas. Okay, this is a nice observation, and there's a good original treatment, classical treatment by Page and Way in 1994, which basically states that if I have a block unitary, then the ways in which I can write out its SVDs requires sort of fewer matrices than you'd expect. So normally if you had 4 matrices and you wanted to write out all of their SVDs, you would need 8 matrices to do this, but they show that you can do it in 4. So it's this nice sort of simultaneous singular value decomposition. And yeah, concretely, you have these 4 blocks here for some larger unitary, and they show that you can find these V1, V2, W1, and W2 such that on this diagonal, these are all, in the central matrix, these are all diagonal, which also kind of satisfy some algebraic relations. So this can also be used to basically show this cubitization argument, if you're so inclined to look at it, and has also appeared in a lot of other useful quantum algorithms work, like this gate synthesis paper by Nora Tan at MIT recently. So if you write out sort of what these diagonal matrices look like, you're going to have this 0 block and the 1 block. These are when the C's have absolute value 0 or 1 I mentioned before, and then you'll have this non-trivial diagonal block which satisfy that basically C squared plus S squared is equal to the identity. And basically these blocks are exactly the ones that are transforming like qubits in the original qubitization argument. So the way that this type of proof proceeds is that you start with a singular value decomposition of just one of the blocks, which we know how to do, and then you're going to compute very cleverly the QR decompositions of 2 other related blocks, which allow you to basically show that these D1 and D2 happen to be upper triangular, and then you're going to chase a whole bunch of matrix elements around this block unitary to show that they're not just upper triangular, they're actually diagonal, and that they satisfy this condition up to this extra sort of unitary freedom we get to choose at the bottom. So maybe if you care about QR decompositions and singular value decompositions, this is more understandable to you, but I think these techniques are quite interesting when it comes to quantum algorithms. Anyway, alternative way, same result. Okay, so qubitization. Let's talk about the limits here. These invariant subspaces are just 1 and 2-dimensional. There's no good notion at the moment now in general of qditization, if you were wondering, although it's quite interesting maybe to trapped ion folks who care about D-level systems. And there is a lot of theory of these so-called general singular value decompositions that come from this Page and Way paper, but they seem to only apply under sort of much stronger constraints on how your 2 operations relate to one another. But it's interesting open work as to whether you can extend these qubitization arguments. And so, questions you can ask is, weaker notions. Can I transform something relating to the Jordan blocks of a matrix? Can I do something related to irrep labels? Or maybe if I have oracles that mark certain subspaces, a lot of people have considered ways to suitably weaken this notion of qubitization. But for our applications, we're not going to need that. And so we're going to talk a little bit about what QSVT has been used for to simplify how we understand what quantum algorithms can do. Okay, so qualified statement that sort of QSP and by nature QSVT, which has QSP happening in all of these small subspaces, is sort of all we need for a lot of quantum algorithms, namely their ability to compute these matrix functions of very large linear operators very efficiently. So here, you have a general A here, there are singular values and singular vectors. We want to apply some polynomial P, and by sort of changing what we're encoding, changing the polynomial, and applying QSVT, we can really sort of mimic a lot of quantum algorithms, usually with improved complexity. So this includes group research, as I mentioned before, which is basically just QSP. In Hamiltonian simulation, if I have some block encoding of H, as I mentioned before, and I apply some function which approximates e to the IHT, this will give me simulation with competitive complexity. Matrix inversion is the same, but I'm approximating the inverse function 1 over x. And I can also do a bandpass function to project onto a lower energy subspace. And so there's this wonderful insight of changing the polynomial seems to change the algorithm, all within sort of one framework, assuming that we can create this block encoding efficiently, as I've mentioned before. But we understand linear algebra very well as a species so far, so it's great to be able to convert a lot of disparate problems into one setting where the well-worn techniques like functional approximation tell you exactly how expensive it's going to be in terms of the degree of polynomial you need relates to the depth of the circuit, and the space requirements are basically just as large as is required to actually contain the matrix within our quantum system. Okay, in practice, mostly people are applying these algorithms to simulation, estimation tasks, and linear systems problems, and then their variants. And QSVT sort of seems to be incredibly useful when you're demanding sort of very precise and coherent answers to sort of specific questions. So if you know anything about the spectrum of your operator, then you can engineer a function which exactly respects that known information, and a la matched filters in classical signal processing theory. But in general, if you're trying to do sort of estimation tasks or exactly determine an eigenvalue, this is not going to give you a faster technique for phase estimation or something which is already extremely optimized because these algorithms already capture BQP complete problems. So if you ask for too much of these polynomials, it's still going to be expensive. If you ask for too much of the block encoding, as I mentioned before, it's still going to be expensive. But there's all these sort of wonderful ways of people showing that you can tweak these algorithms to really give efficient subroutines for, say, proofs of security in quantum cryptography, these nice rewinding subroutines, and also sort of modified phase estimation techniques where you really care about the precision, or you maybe have some promises on how discretized your possible phases are. So a little bit about block encodings, because we can't assume that everything can be block encoded efficiently. And this has been known for a while. Constructing arbitrary unitaries is expensive business. And we also have some constraints, namely that the spectral norm of these block encodings is upper bounded by 1, which means that you're going to need to know at least an upper bound on the spectral norm of whatever you're trying to block encode. And we're also going to have to sort of apply this block, which means we need to post-select on our, being in the image of this projector I mentioned previously. And if you sort of plan this poorly, then maybe that amplification is also very expensive. And in practice, when you actually compute sort of, how many T-gates it takes to do these block encodings, there's still work being done here, and there's some nice work out of MIT Lincoln Lab just this year that basically shows that this can be very expensive, even for small systems, if you don't know anything sort of specially structured about your block encoding, so even in sort of the sparse case. And I'll mention the cases where we can build efficient block encodings in the next slide. There's also some notions about error analysis you have to be careful about. So even if I have an approximate block encoding, the way that error propagates depends sometimes on the function that I'm applying in a special way. Okay, so when is it cheap? A very simple instance of a block encoding you think of as a controlled unitary. So if I have a controlled unitary, then I can easily, that is immediately a block encoding that uses 1 extra qubit of that unitary. But we know in general that controlizing an unknown unitary can be expensive. You can have sparsity assumptions. You can have access to a unitary which prepares a purification of a density operator, which allows you to block encode that density operator. You might have some special displacement structure, so a Toeplitz matrix or a Hankel matrix or something particularly nitridiagonal, etc. Some of these can be efficiently block encoded, and also the quantitative analysis of this is very good. This paper out of Lin's group. You can also have access to free Hamiltonian evolution to give you a block encoding of that Hamiltonian. This is comparatively cheap. And even sort of things like having many copies of a state, which you can use this PCA technique from Lloyd and others to create Hamiltonian evolution by this state rho, which then gives you access to something like a block encoding of rho. So there are many known cases where it can be efficient, but it does need to be shown and is not arbitrarily true. And as mentioned before, there's a lot of these recent papers which have looked at the actual T-gate complexity of these things, and also building programs to optimize over block encodings. And then sort of beyond creating the block encoding, you can think of, as I mentioned before, ways to do algebra among block encodings. So how do I create the block encoding, which is the sum of 2 other block encodings or their product? We've already seen how to do this polynomial transformation. And each of these sort of has many ways you can fuzz it, and people have consistently been making these much more efficient. So it's really quite fun once you get to the block encoding stage of enumerating all of the things that you can do, and using a lot of methods from functional analysis and numerical linear algebra to do these things. Okay, so is QSVT somehow the end of quantum algorithms? And I love including emojis. So this is the stages of grief, I guess, when you're trying to consider whether this is the end. No, obviously. Sort of it works once you've converted your question to a spectral mapping problem, and you've ensured that you have an efficient block encoding. So you should think of it more as sort of a meta-algorithmic framework that is very good at telling you the complexity of a transformation once you've enumerated it. And we also know that it captures local Hamiltonian simulation in sparse linear system inverses. So somehow it's not going to help us on things that we don't already know in the generic setting. Another benefit is that these things are very space efficient, but also sort of highly coherent. QSVT is very much a quantum algorithm for the fault-tolerant regime, unless you're sort of heavily modifying some of its assumptions. I'd say sort of the best thing about QSVT is that it's a sort of very clean abstraction to allow the application of diverse tools from applied mathematics into one setting that tells you very explicitly sort of what the complexity and space and time resources of your quantum algorithm will be. And now sort of a note about dequantization. QSVT can also be thought of in this framework. There's a wonderful paper by Chia, and I think Guillen and Li and Tong and many others that basically show that the normal assumptions in dequantization algorithms, namely the sampling and query axis, or they call it sort of oversampling and query axis, which is slightly different, which is analogous to sort of having QRM assumptions for building your block encoding, that many of these things can be dequantized for many of your favorite machine learning tasks. So you have to be careful if you have sort of low rank assumptions, or if your precision that you require, this paper by Legal and others, if your precision is constant, say in certain chemical simulation problems, then you can basically use matrix sketching techniques to perform dequantization arguments. Which is actually, it's nice from the point of view that it makes dequantization arguments for quantum algorithms much simpler, because it can also use this unified framework, but no free lunch in this scenario either. In practice, these algorithms, have very large polynomial complexities, so it doesn't mean that quantum algorithms can't still be super polynomially faster than their dequantized counterparts, but the dequantization people are pretty good at what they do, and their complexities keep getting lower. Okay, so now I'm going to talk about sort of,
Okay, thank you. The dequantization for constant precision, that's very interesting. What are the minimal requirements on the precision such that dequantization does not apply?
I think that 1 over poly in your system size is still fine.
Mm-hmm. I guess I'm wondering the degree of the polynomial.
I think it's just the precision of the desired, of the state that you're trying to prepare, for instance, or the observable that you're trying to measure. So it's just constant in system size is what they were considering for some chemical estimation problems.
Mm-hmm. But if I had inverse in the number of gates or number of qubits, that would suffice such that
I think inverse poly the number of qubits is enough to make it
any polynomial
BQB complete.
Okay.
Basically. Yeah.
Thank you.
So it's not super strong, but I think for them it's a pretty practical regime for the types of maybe the spectral form factors or some chemical problem that they were looking at. More interesting maybe is this low rank case or the QRM data structure. Okay, so I'm going to talk now about the sort of offshoot of algorithms that relate to something called linear combination of unitaries, which have all sorts of interesting hybrid relationships with QSVT when it comes to solving problems that don't fit so nicely in this spectral mapping framework. Okay, so I'm going to call it sort of the great family of block encoding algorithms. The QSVT is not the only type of algorithm that uses these block encodings. They're useful in other contexts as well. They have all these fancy acronyms. So you've heard of signal processing and singular value transformation. There's something called quantum eigenvalue processing, which does what it says, allows you to transform eigenvalues using some bit of extra space and this thing called these history states, preparation states. They basically solve some nice linear systems problems, which allow them to create these very nice displacement structure block encodings, which then allow them to take very efficiently linear combinations of block encodings, of Chebyshev polynomials of block encodings. It's a little technical, but it's good for certain other problems. So-called generalized quantum signal processing, which allows you to drop these parity constraints. And then what I'm talking about here, which is linear combination of unitaries and linear combination of Hamiltonian simulations, and then randomized variants and parallelized variants. The zoo really goes on, but they're all unified by this idea of dealing with block encodings. So subsystem dynamics controlled very precisely. And the comparison between some of these methods that I'm going to talk about is not always obvious. This can depend even on your architecture or your problem instance size. and I'll talk about some of the major parameters by which we judge the efficiency of these algorithms, but it is quite involved at a certain point. But the basic idea of linear combination of unitaries, which maybe some of you have encountered before, this work by Childs and Wiebe in 2012, was originally formulated for doing Hamiltonian simulation very efficiently in terms of the desired error and time. And one of the basic insights, there's many ways that you can phrase these lemmata, is that if you have some unitary here which pairs superposition, which is weighted by the square roots of these positive alpha sub k, then I can use this to create a block encoding of this operator v up here, which is all these unitary operators u of k, and they're weighted by alpha sub k. So this is what we mean by linear combination of unitaries, and every square linear operator admits such a decomposition as a linear combination of unitaries. Maybe it takes a lot of unitaries. But you can see here that you need two components, namely one, this preparation operation here, which weights our basis vectors by the square root of the desired weights, and then the select operator, which is basically a k-controlled use of k. There's many things that can go on, many variants of this, but you can see now that we take log extra space in the number of terms, and then we also have to make sure that these coefficients are not somehow very difficult to encode into our state. Okay, so LCU is useful for many purposes. Namely, originally in use in Hamiltonian simulation, as mentioned before, you could get down to, if you want sort of this D term LCU, and you want to evolve for some time t, and you have this term alpha here, which relates to the one norm of the coefficients, and they showed you could use log d times this log factor, a number of additional qubits, and then you have this multiplicative dependence between t and this log 1 over epsilon term, also with an alpha t. And the sort of insight of QSVT, because you only want to perform a spectral map and not something more complicated, is that they could drop the number of auxiliary qubits down to just log d, and then the query complexity would be additive in t and log 1 over epsilon. So this is a scenario, time-independent Hamiltonian simulation where QSVT is extremely good at what it does, but if you just look at it from the term of LCU, this is the nature of the improvement. And then the nice aspect of QSVT is that it's very efficient to approximate entire functions, namely functions which don't have singularities in the complex plane, by polynomials. So the expansion that they used in QSVT is the Jacobi-Unger approximation for trigonometric functions, and these are very, very good and fast approximations. And basically, if you compute the one norm versus the infinity norm of these functions, QSVT depends on the infinity norm, and the LCU will depend on the one norm, which in general grows as the time of the simulation. Okay, so yeah. Yeah.
Does this mean that QSVT is just better than LCU?
For time-independent Hamiltonian simulation, you can get this additive dependence between t and 1 over epsilon. So in that case, it is better. But for the time-dependent case, or let's say that block encodings are very expensive to prepare, as it might be on a near-term device, then there may be reasons even to use Trotter over some of these other methods. But at least, yeah, for this simple case, QSVT is currently the best at time-independent Hamiltonian simulation with good block encodings. But in general, you might have some time-dependent problems. So this nice linear differential equation with maybe some inhomogeneous term here. These are all vectors, and A is some operator. If you're in the world of differential equations, then you can see that if you want to approximate basically the evolution according to these dynamics, you're going to need this time-ordered integral. And notably, this is not going to be some spectral map applied to A, because your eigenvalues and your eigenvectors are all messed up in this setting. And so basically the insight that these more recent methods came up with is that I can still actually write this unitary as a linear combination of Hamiltonian simulation operators, basically by approximating this integral through quadrature. And the insight that these people made is basically you have all these nice integral identities, and these exist throughout physics. Namely, I can approximate this e to the minus x function in terms of something whose inverse Fourier coefficients are something like e to the minus x. And if I assume that this f function here also sort of sufficiently decays its Fourier coefficients sort of sufficiently decay, then this integral will be convergent, and I can also elevate this to become an operator-based integral equation. So the idea here is that we'll now have L and H, which could in general be time dependent, where L is the Hermitian part and IH will be the anti-Hermitian part. And we can show that this converges to this integral over here, where now L is weighted by some factor k, and F here is something where its inverse Fourier coefficients decay sufficiently rapidly. What we're going to do is basically approximate this integral by many different pieces, and each of these pieces is going to look like Hamiltonian simulation by a time-independent Hamiltonian that's also Hermitian. So this k vector value here, if I hold k constant, you can see that I'm now basically getting rid of this I dependence. Maybe I swapped around a couple i's here. But the point here is that it's very easy to evolve by Hermitian Hamiltonians with QSVT. And so we want to take a linear combination of these Hamiltonian simulations to approximate this integral, which, if we know some nice things about this function f, will converge very rapidly. So the complexity of this simulation in this time-dependent case is now going to basically be once again multiplicative. There's no known sort of additive lower bound even. It's very much an open question as to how expensive this will be, as well as this sort of UR factor, which depends on basically how our state vector evolves. So the properties that we're going to need on this f, this kernel function it's called, are going to be chosen, as mentioned before, to have Fourier coefficients which decay sufficiently rapidly. And basically the inside of this most recent paper by Lo and Soma, which improved on results of Dongong and Lin, is that this sort of Fourier decay doesn't need to be in the entire upper complex plane, but only on sort of an infinite strip. So in the world of complex analysis, it's it's very nice to compute integrals and contour integrals in terms of properties of their poles. And so basically they choose a different contour integral, which has slightly nicer convergence properties. I should mention that this integral quadrature can be quite technical, and so this also had to be showed, namely that if I split this thing into a whole bunch of smaller parts, each of which looks like a Hermitian Hamiltonian simulation, I need to make sure that this actually converges well for a reasonable choice of quadrature. And they show basically that you can use a uniform discretization of your integral. These methods, I think, are quite extensible, and I think it's just sort of beginning now how we're going to use them. And you can go sort of beyond just generic time-dependent Hamiltonian simulation to also sort of linear system solving. And so there was a paper recently where they solved this Sylvester-type equation, this linear matrix equation, using a similar technique in linear combination of Hamiltonian simulations. This could be actually converted to a normal matrix inversion problem, but they show basically that they can avoid this to save the space and also the subnormalization factor. So there's a lot of interesting algorithms that go beyond the spectral mapping framework is mostly what I intend to say. I'll talk a little about linear system solving, another big application that people are interested in quantum computing. And QSVT sort of is not the leading method here currently because it has this subnormalization condition we have to care about. And there's a whole series of work which looked at this in various settings, including sort of the original Hare-Hasidim-Lloyd algorithm, which has this inverse Pauli dependence on the error, as well as the square condition on the squared dependence on the condition number kappa. And the squared dependence is also shared by QSVT, primarily because we're trying to block encode A inverse, which means that we need to subnormalize our function by kappa because our function has to have infinity norm upper bounded by 1 on this interval, which means we also have to do order kappa amplitude amplification, which means that at least without heavy modification, this kappa squared factor is not going to be removed by QSVT. There's also a log kappa factor that floats around here, which is even harder to get rid of, but I won't talk about that here. This VTAA here, this variable time amplitude amplification, is also sort of known to give us asymptotically this complexity, but I think the actual quantitative gate calculations of these methods, people haven't done a lot of end-to-end computation. So in a practical setting, if you want to invert a matrix, I think it's still very much open as to which of these lower methods you should use. But it's interesting, and I think that it's not totally unreasonable that variants on this LCAHS methods I talked about before might be able to improve on this further. Okay, so here's just some rules when you're thinking about relative complexities of QSVT or LCHS or LCU methods. QSVT really cares about this infinity norm, so the maximum modulus of your function on this interval -1 to 1, whereas LCU really cares about the 1 norm of the Fourier coefficients. Yeah, the function that you're trying to implement, you can talk about its infinity norm on the interval, or you can talk about the 1 norm of its Fourier coefficients. Bounded approximation also is slightly more expensive than just sort of standard approximation to a function. So the fact that we have to, eliminate, the Runge phenomena in our, if you're trying to approximate some bandpass function, is also going to introduce usually a logarithmic overhead in whatever precision you're caring about. And then, space use in LCU is generally not constant, but once you have the block encoding in QSVT, you usually don't need to use additional space unless sometimes you need constant extra space to get rid of these parity constraints. And then in the problem of Hamiltonian simulation, which gets even more involved, you have generally dependence on the spectral norm of the Hamiltonian, but there are also a whole family of methods based on trotterization and these multi-product formulas which have commutator scaling, which is in general very difficult to compare with these methods. And you also have other sort of nice experimental constraints, namely that these Trotter methods are usually in place. You don't have to worry about block encodings, and maybe you have natural access to free Hamiltonian evolution by some subterms. So each of these sort of has to factor into which method you actually intend to use beyond just the asymptotic scaling. There's also sort of debate, and I think people have different opinions on this. So QSVT and Hamiltonian simulation and other estimation tasks, you have this log 1 over epsilon dependence that appears, but every time you're trying to get information out of your state and you actually have to do some estimation tasks, then usually this 1 over epsilon or 1 over poly epsilon complexity is going to reemerge unless you're using it as a subroutine to feed into another quantum process. So just statistical methods are going to mean that the reality of this log 1 over epsilon dependence for preparing a certain block encoding is debatable in practice. Okay, so a little bit about open opportunities in the near term. One, as I mentioned before, is sort of moving beyond spectral mapping. So both talking about the connection between these integral equation methods and manipulations of block encodings. Another is just thinking about access models that are not necessarily as strong as a block encoding. I mentioned before that it's very difficult to black box controlize a unitary. And there's also been work on sort of, can I create the black box of some matrix representation of a quantum channel, only given access to that quantum channel. This can in general also be very expensive. And also sort of the so-called hybrid methods, namely, am I using LCU to create my block encoding that I then apply QSVT to, or have a trotterization step in the middle, and you can imagine all different manner of ways in which you stack these methods. Or, for instance, there's work that talks about continuous variable, hybrid continuous variable, discrete variable quantum systems, then is there a reasonable way in which I can talk about variants of QSVT in these systems? And then third, and this is also related to sort of a personal interest, is that the way that we currently prove, say, the achievable functions for a given QSP, like circuit ansatz, are quite inflexible. And you might sort of ask if I were to change this ansatz, or to maybe examine some other structured parameterized quantum circuits, is there an easy way to functionally characterize, say, what it has achievable as a matrix element? And right now, QSP methods are quite rigid in that regard. So yeah, these are other examples of these three areas. I also, it's great to have end-to-end analysis. There are some limited ones coming out now, but basically, there are a lot of opportunities to be optimistic in QSP algorithms if you know any sort of side information about the spectrum of your operator, or you admit, small amount of error, or if you only care about, approximate notions of operations between block encodings. Then I'll talk a little bit about relations between this and machine learning tasks. The first, as I mentioned before, is maybe not sort of a positive realization, but a lot of these dequantization proofs can be simplified and unified through QSVT methods, which I think have a nice presentation in this paper by Cha and others. And there's also been sort of separate lines of work that look at quantum circuits as analogs to certain sort of, together with certain universal approximation theorems, and you can sort of recognize QSP as some notion of a universal approximator in a single qubit. And you can start talking about, if I modify the statements of these types of theorems, how do I show that these universal approximators are efficient, and how do I optimize over them and whatnot. And then finally, there's sort of more direct use of these methods, I think also from people here at the National University of Singapore, for certain things like the inference step in transformer models. And so for other types of matrix manipulations that you might want to do beyond just matrix products, like element-wise products, these Hadamard products, et cetera, these all need to be, for the very least, investigated. It may be very difficult to train, the quantum analogs of some of these devices, but at least for the inference step, there's quite a bit that you can do to extend QSVT-like methods to understand how to manipulate linear data efficiently on a quantum computer. And as always, beware with unqualified machine learning statements for the reasons mentioned before. You still have to input these linear operators on your computer efficiently, and measurement still needs to be efficient. And if you assume too much about how you're inputting your data, then these things can be dequantized. Okay, so final message. I think I'm keeping it relatively short. Yeah, QSP and QSVT are just sort of one instance of a larger family of algorithms for manipulating these block encodings, so very sort of efficiently controlling subsystem dynamics, which is quite interesting. So the whole operation is unitary, but what's happening in the subsystem is non-unitary, and this gives you a lot of freedom to do things like very non-reversible transformations of that subblock, like matrix inversion or applying a bandpass function, for instance. And these algorithms are very friendly to methods from classical signal processing, from numerical linear algebra, et cetera. And almost all of them, if you make some assumption on your data or the spectrum of your block encoding, then it can almost always be leveraged to improve the complexity of your algorithm. And basically the settings in which some of these methods for manipulating block encodings outperform one another are constantly evolving. And so when you ask me sort of the best method currently for, say, linear system solving or Hamiltonian simulation, it can really depend on your architecture and what sort of the natural operations you have access to are. And we still sort of have very limited instances of ideas like qubitization for controlling these sort of nonlinear subsystem dynamics. So we talk a lot about QSVT as being a great unifier of quantum algorithms, and I think this more reflects the fact that a lot of quantum algorithms look somewhat similar under the hood, rather than the fact that sort of this is all the quantum algorithms that can exist. And as we've seen before, sort of this unitary framework that QSVT is built on is not always amenable to the natural types of transformations you might want to do, like time-dependent Hamiltonian simulation. Yeah, and the takeaway is I think that there are ways to be a hell of a lot more optimistic about these algorithms. Namely, every time you assume some sort of side information about your data, or for instance, if you only care about Hamiltonian evolution on some nice subspace, there are probably a lot of ways in which these algorithms can be modified to drastically improve the resource requirements. But yeah, I think that that's it for this. Yeah, and as mentioned, these slides with all their references are online, and I'm happy to take any questions.